All right, folks, thank you all for coming. It's about 4 o'clock. I'm going to bug you for about 45 minutes, roughly. My name is Soham, and I happen to run a very small business in Sunnyvale. It's about preparing for technical interviews. Yeah. And I have been coming to these workshops for several years now. Peter, the founder, is a friend of mine. Today, we are going to do a little bit of recursion and dynamic programming, right? Because that often happens to be the linchpin when it comes to technical interviews. Before we get started, I want to get a little bit of a read of the class. How many of you are in college or just graduated from college, roughly? Okay, good. And how many of you are actively looking? Everybody in college? Or at least half? Okay. How many of you actually want to crack into a better company or a good company? No, I know many hands go up with this question, but you know what is surprising is that not all hands go up. Not all hands go up. Even though it's a very obvious question, right? Do you want to work at a good company? Some people are like, I don't know. I don't know. And there are many people out there. I mean, obviously, depending on what life stage you are, you may or may not want to work at some of these companies. Okay? But generally speaking, I am of the view that when you work at a better company, and the sooner you crack into a better company, the better it is for you in your entire career. These companies, good companies, better companies, they give you two things. One is they give you an intellectually fulfilling job. Right? People around you are good. They are very driven people. Right? They're not necessarily people with 180, 200 IQs, but they're very driven people. When you surround yourself by driven people, you actually do much better, right? On an average. The second thing they do is that they give you a financially fulfilling offer. Right? Some of these offers are extremely good. I'm not sure if you have ever looked into some of these numbers. Right? Out of college, 150 is normal at many of these top players. Right? Out of college. Half the America doesn't save 150 for retirement. Right? You realize that. But companies like Google and Facebook will pay you that at age 21 in 1 year. So, in general, it is a worthy goal to have, to crack into a good company some point in your career. The issue in having that goal is really got to crack into it. Right? It's actually not trivial to crack into it. Right? Obviously, once you go in, you're not going to make it easy for everybody else to come in. Right? Yes or no? Yeah, of course. Okay. Needs sustained hard work. This is what we do. This is my profile. I used to be a director of engineering at Box. How many of you know Box? How many of you know what Box does? Somebody explain it to me. Just one line. I don't need to spend more time on it. Just something. Yes, cloud storage for enterprise. Right. If you have ever worked with SharePoint, Box does that in the cloud. So I happened to be joining them very early. I was their 5th engineer when I joined. And I grew with the company for about 4 years. And after that, they made me a director of engineering. And I stayed in the role for a couple of years. Through my journey at Box grew manifold. When I joined, we were 15 people. When I left, we were 1,100 people. And a lot of them were engineers. When I left, about 350 of us were engineers. So I was very fortunate to have an idea of how the interview processes work. I had a hand in setting the interview process and among many other things. So when I left, I realized I wanted to start my own thing, figured this is probably the best thing to do. Because there are many, many smart people out there, or they simply don't know how to prepare. Really just that is what is standing in their way in cracking some of these very good companies. Box's offers are also as good as Google's and Facebook's or practically any other place you can think of. Right? When I am there and I know that I'm making a $250,000 a year offer, I'm not going to give you an easy exam. It's very simple. And it's a competition. One has to prepare for competitions. So anyway, that. Currently, this is what I do, very standard education, right? MSCS. Here is my interviewing experience. I've conducted countless technical interviews. Scores of offers extended from my budget, where I had to make agonizing decisions on who actually to make an offer to. So evaluate interview results, compared with other candidates, right? Figuring out if the interviewers have done a good job at this and stuff. I've helped companies set interview processes as well. I helped headhunters screen candidates and managed interviewers and coached hundreds of software engineers by now from the course. I've not written books. I've not made any fancy presentations, as you can tell. But I happen to know practically everything there is to know about technical interviews. Not to mean I know everything about technical questions. There are many that I don't know, and it's always a moving target. But I've lived through a lot of nuances of this process, right, on this. So one thing is very clear to me, that the biggest bottleneck in clearing technical interviews is really recursion. Many people are good at linked lists, trees, and stuff like that. But when it comes to recursion, it becomes challenging. Can anybody tell me, or let me back up a little bit, how many of you have never heard of recursion before? This is like the first time, like a bombshell, first time you're hearing about recursion. Anyone? Awesome. Why is recursion hard? Or why can it be hard? For some people it is very easy. It's just naturally sometimes tuned to that. But for most of the people, including myself, it was hard. Why? Hard to visualize. What else? You have to adapt to it. Yes, you have. Things happen behind the scenes. Yes, very good point. Yes, time complexity, yes, certainly. The time complexity is sort of less of a thing in recursion because nearly every single time, except when you're dealing with just trees, nearly every single time complexity is like bad. You know, just exponential, and you can put factorials and you can raise to n's and all that, but it's really just bad, basically. But yes, questions? Think about depth of the stack, correct? Backwards? Is it always backwards? Works both ways. Yes. Yes? Identifying that this is a recursion problem. Interesting. Yes, breaking into subproblems. Yes, correct. That is the point. Yes. Look, we do many hard things in our lives. Driving is not an easy thing to do, right? But you still take the damn car out every morning and go. It's a risk to your life. This is not a risk to your life. For no fault of your own, you may be hit. Well, like in driving and many other things that you do which are actually categorically life-threatening. They're hard to do. But we are good at it. Right? Not this thing, why? Because we don't do it every day. We just don't do enough of it. We don't think like this. Right? We don't think recursively in our lives. We don't like go and break things into subproblems all the time. Just don't. Our thinking, human thinking is extremely linear. This happens and then that happens and then that happens and that happens, and the moment we have like a branch out to say, I can take that decision versus that decision, blows. We can't actually think like that far. Every time there's a decision tree and a decision to be taken, It's cognitive load. If there is cognitive load in simple decision making, think about cognitive load in recursive solutions. And then so what happens is mind always takes easier paths. Always. If you have two choices, one is harder than the other, you'll always pick the more convenient, more easy path. So whenever somebody presents a recursive problem, your first thought is like, why is this a recursive problem? Why can't I just do it iteratively? Like so many ways of doing it, what the hell? Right? And then right there, your half the mind is gone. Practice. Really, that's all that stands in your way, nothing else. You have done harder things in your life, but you've done it more often. That's why. That's why you're good at it. So the only thing you got to do is believe in practice and do it. Some people will need maybe 20 problems, some people will need 200 problems, some people will need 2,000 problems. You know what? It'll happen. The easiest way to learn recursion is via trees, binary trees, to be more precise. You know why? Guess? Every node has a subtree, yes. And so, can you verbalize it more precisely? What is the benefit of having a subtree? Correct. And it's a repetitive process, and more importantly, they're connected. But the whole problem in recursion is to break it down into sub-problems, while a tree that gives you readily. Because it's a subtree right underneath. Right? The issue in recursion, as I'm sure some of you or many of you have tried, is to take a problem, break it down into smaller ones. Right? You can see that the same problem that you see that the interviewer is giving you, you need to see a smaller version of it in order to solve it. If you have a tree, you really already see the smaller version of it because there is a damn subtree there. You don't have to really think about it. Versus if you are reversing a linked list, it's not that obvious. Where is that subproblem? Versus if you are given a string and then there is string recursion, it's not very obvious where is that subproblem. In a tree, very obvious what the subproblem is. Subproblem is the exact same problem but on the subtree. That's all. So your easier bet to learn recursion is via trees. We will take one problem today. Right? And then that will make some sense. So ideally, I would have had a whiteboard, but I think we'll make do with slides today. It's a basic structure of a tree, a binary tree. Okay. Nothing too fancy. Anyone who doesn't know what a binary tree is? Very good. All right, let me ask another question. How many of you are not from computer science background? Not from computer science background, CS background, any formal CS. Okay, good. That's fine. CS is one of the very few fields that invites people from everywhere. You don't need a CS degree to be a programmer. All you need is a computer, and you can learn anything. Right? Versus mechanical engineering. There's no way in hell you can learn anything about wind tunnels sitting at home. Right? No chance. Chemical engineering, you need to build a lab. Right? So it's a very, very special field that we are in. Anyway, so tangent. Okay, so this is a binary tree. A problem is this. Let us find the height of a binary tree. It's a very simple problem. Once you are practiced, not before practice. Once you have practiced enough, the solution to this problem of finding the height of a binary tree is expected within 10 minutes, including the delivery of the question. You are asking any more questions about it, you putting the code on the board, debugging it, all the way through, 10, maximum 15 in an interview. Okay. They don't tell you that. No. Then the interview wouldn't be an interview, you know. There are different views to that. I mean, there's no sort of unique view to all that, but generally speaking, this is a warm-up question in interview. Very simple. It's a binary tree. Just find me the height of the binary tree. Some of you obviously know it. Those who have practiced and prepared, you generally know sort of how to do it. But let's hold the horses. For those of us who are not able to see it that quickly, those who are not yet practiced, simple. Let's go through it a little bit slowly. Okay. So this is a tree structure. In a tree structure, the easiest way to do recursion is to ask questions. Now, the problem statement says, find the height of a binary tree. What is height of a binary tree? How many levels there are? Now, does the tree need to be a full and complete binary tree for that? What is a full and complete binary tree? Except the bottom layer, everything has a node. It's like a full, complete tree. Right? So you don't see a missing node here and there. So sometimes those who have not practiced enough, they assume that the tree is full and complete. It's a very naive assumption to make. But when that happens in an interview, I understand that somebody hasn't practiced. So this tree could simply be, at an extreme, it could simply be a linked list. Is that possible to visualize? If there are, say, no right nodes, everything is left. It's still a tree. It can be imagined as a tree. Or it could be anything in between. It could be as large. It may not just be 5 nodes, 6 nodes, 7 nodes, millions of nodes. Right? By looking at it, you can't tell the height of a tree. So, mic drop? No. Okay. All right. So how do you tell the height of a tree? Okay, what is the difference between height and depth of a tree? Height and depth. Height is depth minus 1? No, they are the same. Just the same. Computer science is a very funny place. You know? Trees actually grow downwards. The root is at the top and the whole thing grows downwards. We imagine it like that. Right? Computer science is actually very, very funny. Like we kill children. Right? We delete children. That never happens anywhere else. Anyway, so coming back to the tree. Height and the depth are the same, just really depends on where you're looking at from. Okay. So in recursion, or let me back up even a little bit more. How do you know that this is a recursion problem? Given a binary tree, find its height, find its depth. How do you know that it's a recursion problem? It repeats. First of all, it's given on a binary tree. So the best way to traverse a binary tree is through recursion. What is a brute force solution? Let's say for a second you couldn't imagine what the solution would be. What is the brute force of this? Start from the root and go hit the null nodes or the leaf nodes, you're saying. So start from the root and go all the way down. And say, okay, now there is no more. And then you go back again to the root and you go yet another path all the way down, right? And say, okay. And as you keep going, what do? Count. Like next level, right? So you go all the paths, right? Keep going back to the root. Keep going back to the root. What is the issue there? I mean, it will work, right? Easily work. What's the problem?
Yeah, the issue is that you're wasting your effort because you're recounting things that you've already counted.
You recounted things that you already counted. Excellent, yep. So that, and many of you may have attended Gail's session earlier. Right? She does this beautifully well. Right? Find repeated work. Right? What is repeated work? Go to the top and go all the way down. Go to the top and go all the way down. Like just counting it again and again and again and again. Like why? Okay. So we understand it's inefficient. What is more efficient then? What is a more efficient way of thinking about it? We understand it's a tree structure. So some sort of breaking down into subproblems is required. We understand that we need to do better than the brute force solution. We understand that we are repeating a lot of work here. So how do you think about it now? What are some sort of subsequent thoughts? You can save those in the nodes. Would that work? Because you would have different height at every different node, right? So you would have to save all the heights, right? So if you are given a node, there might be different heights, like different paths to that, and so you like to save everything. Yes, you had a thought? Right. Yep. Very, 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 very good thought. Any other thoughts around it? Questions? Yeah. Where do you start in that method? Okay, and then? So how would you maintain state of, what would you maintain a count? Right. A key question to ask, where do you start? Let's start at root. Usually trees start at root. Right? Then, what is the height of this thing? Right. Make the observation that height of this is height of my children plus me, whichever is larger. I'll ask my left subtree to say, what is your height? Tell me. Ask the right subtree to say, what is your height? I'll add 1 and I'll send it to my parent. If I'm starting at root, I don't send anywhere. That is the answer. It's simple thinking like that. We are not unfolding this entire thing in our heads. One very big mistake most people do is that people unfold recursion in their minds. The moment there is some sort of a recursion on the board, they try and say, oh, it's called, and then as you are unfolding it back, you lose track of things. Never do that. You could do that once or twice if you just want to understand what the stack looks like and what is the state at each level. But that is not how recursive problems are solved. Recursive problems are simply solved by asking the question, where do you start? What question do you ask to your subproblems? So you start at root. Start at one point, you root. Then the next question you ask is, what is this? What is the question I'm trying to answer? Height of the tree. Take that same question, ask your children. What is your height? What is your height? once those guys tell you, do all your processing. Okay, I need to find the max. Add your height, return it to your parent to say, okay, this is mine. When everybody does that through the whole thing, problem gets solved. Very simple. Do not unfold. Figure out where to start. Figure out the sub-problems and ask a question. What question to ask is very simple. It is the same question that interviewer asked you. Right? Straightforward. What is the height? You say, tell the child, what is your height? What is the child going to do? Ask all children, what is your height? What is your height? Goes all the way down, then what happens? There's no more children. Right? Null, 0, 0. So, right? I don't have a child, I don't have either left or right child, so the height is 0 from those. Plus 1, myself, I am the first level. Right? Child doesn't know first level or whatnot, does only plus 1 and returns. Then the parent says, okay, your height is 1, this other child's height is 2. What is the maximum? 2. You make a local decision. At every level you make a decision because you don't need that information afterwards. Right? At every level you make decision to say, okay, this is 2. Right? Then I'm going to add mine, 3. Go up. The parent up says, okay, you are saying it is 3 and the other guy is saying it is 3. It's the same. Great. Common. Right? Maximum is 3 plus 1, 4, return. We don't need anything else. We don't, right? Remove all the unused things. Really figure out what do you actually need, what do you not need. If you don't need, is there a way to not use it? Trees and recursion, they map them onto themselves very, very well. I almost cheated with you though. The reason I'm saying I cheated with you is because the hardest part in recursion is not to know where to start, not to know which question to ask, not to know what to do, what processing to do, not to know what to send to parent. Hardest part in recursion is, that's not even the hardest, but we can discuss that. In this question, where did you stop? At the leaf node. Yes, every recursion should have a stop point, otherwise you'll overflow. Yes, that is an important thing, but it is hyped up as an important thing. It is not the most important thing. The most important thing is to know what are the sub-problems. In a tree structure, we almost cheated. Right? We knew what the sub-problems are. They are just your subtrees. Right? So the practice you need is obviously sure in finding out the base case, finding out where to start, finding out what question to ask. Those are relatively straightforward. The biggest practice you need is in figuring out what is the sub-problem which looks very similar to the question that I am asking. No, you're thinking about it completely opposite. When you look at the problem, the first thing that jumps to you after practice, first thing that jumps to you is that there are sub-problems here. Once there are sub-problems is when you apply recursion on it. It goes the other way around. You look at the problem, you look at the question which is being asked, and you say, is there any way I can break this problem down such that I can ask the same question that the interviewer is asking on a smaller problem? If yes, recursion. Yeah. It's not like a recursion problem. Recursion is merely a hammer on a nail. One of our instructors said it's a giant hammer for a very small nail. but that you know when you practice a lot. So again, start at the root, ask the question, tell me your height. Right? You tell me your height, you tell me your height, I'm going to do processing, return to the parent. So the code for this is really very simple. 5 lines. Literally 5 lines, even for a million node tree. The crux of this code is really just 1 line. That is the crux of the code. Rest all is housekeeping. Sorry. Yeah. Rest is all housekeeping. And every child is answerable to the parent. Remember that. Right? You're answerable to your parents and your kids are answerable to you. Same thing in recursion. Nothing fancy. Exactly. You're looking for that 0. Once you have that 0, you just keep bubbling up. And at every level, you don't need to store all the heights, right? It's just one variable all the way through. You don't, right? The interviewer did not ask you to store all the heights and figure out which is what. The question was, what is the height of this given tree? That's all there was to it. Given as a word problem? Okay. Yes, it is. That is the problem. That is what needs practice. Rest all falls into the place. Rest all falls into place. That is the part. Like, can I break this into sub-problems enough that I can apply the recursion hammer and do it? Okay. What is the time complexity of this thing? In terms of number of nodes. If a tree has n nodes, what is the time complexity of our solution? O of n, order n. Each node is visited only once. We are only visiting each node once. But that is not typical of recursion. Recursion is usually very wasteful, except in case of binary trees like this. That is why you prefer recursion for trees, because there is no waste and the code is very succinct. If you did this with a stack, which obviously you can do, right? Recursion is merely syntactic sugar. Right? Behind the scenes, the runtime maintains a stack, which is for you just maintains a stack. That's all it does. If you did this with a stack, it will take you 45 minutes to do it. And then you'll accept recursion as gift. So, don't. All right, let's keep moving. Dynamic programming is a really silly name for something really simple. It's merely caching something. There is a hype for dynamic programming. Half of the hype is because the name has nothing to do with what we do inside it. This is where you know naming matters. This is where you know naming matters. There are many people who think of dynamic programming and they can't make the connection to the next step. Question? Yes, recursion usually goes top down, but DP goes bottom up. Yes, but something like that would have made an amazing name. It's something like bottom up iterative approach, then you know what anybody's even talking about. This was a marketing thing. Anyway, here is a matrix. What is the value of the highest value path? You're given origin and destination both. Origin is the top left, destination is bottom right. This is a very canonical dynamic programming problem. Canonical. What is a canonical? What does canonical mean? Very basic the textbook problem. Textbook dynamic programming problem. This is also less than 20 minutes on phone. Okay? But only after practice. Otherwise it is 16 days. I'm exaggerating, sorry. But so the idea is you have to find the highest value path. Right? Actually not the path, the total value of the highest value path. In its simplest form, you are given a matrix like this with all the positive numbers, origin, destination at the two ends of it, two corners of it. The question is, how do you find what is the value of the highest value path in this? Right? And sometimes it is formed in different ways, this is like fishing things, and each cell has number of fish and things like that, and you want the maximum number of fish as you go from origin to destination. Which path will you take and how many fish will you collect and stuff like that. There's variation of Manhattan taxi and things like that. All boils down to just this. So obviously, I mean, this is a small 4 by 5, right? 5 by 4. So you can try and do the math and say, no, right? So just sitting here.
Is there a maximum number of cells to visit? Otherwise, you can just visit every one. You got the math.
I know, right? You can only go right and down. You can't go back. You can't go diagonally. So you cannot. So you can go right and you can go down when you traverse from origin to destination. You can go to the right. You can go down. You cannot go diagonally, and you cannot go back. Yeah, right? That's the constraint. But let's admit that actually figuring out the total value of the highest value path is not trivial. This is 5 by 4. If I give you 500 by 400, there's no way in human hell you're going to do this. Right? That is why there's computers. And that is why there's DP. Right? So now let's look at this. I want you to shift your attention from numbers. Shift your attention away from numbers. Numbers really don't matter. What is our goal? We just want to find the highest value. Right? Whatever the number is, we're just going to add those things. Simple. So again, look at this. Start somewhere. Where do you start? Start somewhere. Start with a cell, random cell, me. You could start really anywhere. The question to ask is, again, I'm trying to do this in a recursive way. Can you see the recursion here? Can you see the sub-problems here? The way at least I have drawn it? Similar to a tree. Yes. Yes. I put the dynamic programming slide, but if I had not put it, would you be able to see that this is just recursion? What is the recursion here? What's the recursion here? Yep. You can go left and right, right? Right and yes. If you just imagine it's tilted, then it becomes left and right for you, right? Right and down otherwise. We know the question to be asked. What is the sub-problem here? Yes, but slightly higher than that. I think you gave me a little bit more granular answer. Give me slightly higher on that. Right. The original question is, when you start from origin and you want to reach the destination, what is the maximum value? Right? The sub-problem is, when you start from this blue node, me, and you go to the destination, what is it? A random blue node, any node, and you reach the destination. Right. What is the highest value path? If you knew that, can you do other things? If you knew what is the highest value path from here, let's say this cell, to the destination, would it help? Or help? Right. Similarly, as we saw in the previous tree problem, if you knew what your children are telling you, you know what processing to do. Exactly the same way, if this is a random node, me, if your right child is telling you something and down child is telling you something, if they both give you the highest values from paths originating from them, right, you look at them, you find the max, you add the value that you have, and you tell it to your parent. That is a recursion. It's exactly a tree. Again, just a different representation of a tree. And again, we are not even saying it's a dynamic programming problem. At this point, we are only on recursion. There was a reason I said recursion and DP, because they are in continuum. Once you have the recursion in your hand, DP is actually fairly straightforward. Very, very straightforward actually. But I need you to come to that realization in a different way. Solve it as a recursion problem, which is exactly the same as finding the height of a tree. The recursion is precisely the same. You pick a random node or you pick the origin node, root, doesn't matter. What question do you ask? hey right child, tell me what is the value from you. If I take my path from you, what is the value? And the down child, if I take my path from you, what is the highest value from there? I get two highest values, then I know how to compare, I know which one is higher, and I add mine, and then I tell my parent, look, if you start from here, the highest value path is this. The value of the highest value path is this. If the parent then wants me to figure out the path, we'll figure out the path. It's trivial. At this point, only the total value is expected. If the only total value is expected, you ask the two children, tell them to figure out their own, do your processing, send it to a parent. How would the children figure out? Children will ask their own children, right? So guess what happens? Anyway, so this is straightforward. Left child, right child, me, answerable to the parent. Right? Same recursion. Instead of +1, it is plus me, whatever the value is in me. It was 3 or 5 or 6 or 7 or 10 or 4, whatever it was. Sending it. Now, the right and the down children, right? They will ask the same question to their children. Yes? So what will happen is that both of these will ask the same question to a common child. They have a common child, the orange cell. Yes or no? Right? So the right cell would say, you tell me, and the down child, you tell me. Right? The down child for the right is the same as the right child for the down in this construct. So this orange guy gets asked the question twice. Right? And this is not multi-thread programming or any of that. Right? So one time it gets asked, it finds the answer. Second time it gets asked, it has to find the damn answer again. Yeah? What does this orange guy do to find its own answer? Ask its own children. You tell me, you tell me. I'm going to do the same processing and send it to my parent. Right? So the first call goes from the blue to the right to the orange to its children all the way to destination. Right? And then comes back, and the second call goes to down to the orange to its children all the way to destination and back. Is that understandable? You write 2 lines of code, right? You'll make a call to the right child first, and you'll make a call to the down child second. Either way, order really doesn't matter. But in the process of making those 2 calls, you had repeated work. There was no repeated work on the tree side because it was actually a binary tree. This is the graph masquerading as a binary tree. Yes, because there are common children. So processing on a given node is done, and then another call is made on the same node, and the whole thing goes again. So the entire recursion goes all the way through destination again. And this is a 1,000,000 node graph. You're doing a lot of work. Your code still is 5 lines. Recursive code is still 5 lines. But the work you ended up doing is humongous. Your servers in the backend will just hog. Right? Because over and over again, they'll keep making the calls again and again and again for the same answers. And they will go all the way down, right, bring you the answer. All the way down, bring you the answer. Not very smart, is it? That is what I want to see in interviews. I want you to have this insight, that you're doing a lot of repeated work. I don't want to hire you, and I don't want to look over your shoulders to make sure every time that every single line of your code is not doing repeated work. I want you to have that insight. I want you to have that urge in an interview. I don't want to babysit you. I have so many other things to do. Right? You're not babies. I need an urge for efficiency in the interview. It is a different story that some interviewers take it to a pervert extent. They're not really thinking about it, but that is the whole point of interviews like this. So find out that repeated work. Now what can you do? Now you know that this cell is being called so many times. The question, tell me your highest value path, and tell me your highest value path. What do? Cache, right? Caching is actually the only thing that really improves any sort of efficiency. Cache. So what you do is the moment you have answer for any cell, you cache it. And as you cache it, What is the, how do you cache it? What is the key? What is the value? Key is the node, right? Node could be indexed by anything. It's a 3 by 3. Node 3 times 3, third column, third row. What is the highest value path from here? That's your value. Similarly, the whole thing is cached. The value from this node is cached, and this is cached, and this is cached, and this is cached, everything is cached. You could argue that, hey, this is not called multiple times. You know what? Doesn't really matter. Still cache it. You're not really wasting too much. So don't let your mind wander into too many edge cases at this moment. Your first thing in a recursive problem, even a DP problem, is to figure out your main recursive condition, not the base cases. I know the world tells you to figure out the base cases first. Good, if it is easy enough, go quickly do it. But 90% of your effort is really in the main case. What is your main recursion? Right? So cache the whole thing. There's a term for that. What is the term for that? Memoize. Memoize. Right. Put it in the memory. Instead of calling memorizing, just memoize. Just fancy, I think. Nothing else. So, right, now can you understand how it flows? Second time there is a call, you check in the cache first. For this cell, have we already done the damn work? Then don't do the damn work. Just return. Now, right, this is what your cache, a pair in your cache would look like. This key, whatever the best path value was. Can we do better? Yes. Why not fill the grid from other side, bottom up, right? It's very straightforward. Actually, when I present it this way, it'll feel straightforward. Why don't you start from the other side? If you start from this cell, you know what the highest value path is to reach to destination. There's really nothing. You can only take one hop. Correct? If you start from that 2 up there, you know you can only go down. The highest value path is 6. Highest value is 6 if you start from 2 on the other side. So you start filling like that. Once you have the answer for 0 and 2, the answer for 8 is straightforward. What does 8 say? Hey, Mr. 2, tell me what is your path. Mr. 0, tell me what is your path. 6 and 4, what is higher? 6, I'll add my own, 14. If you go through me, right, the cell 8, then you can collect 14 fishes. 8 from here, 6 from one of my children. Similarly, this is straightforward, right? Because you know this. You can't go up. Remember, you can't go up, you can't go backwards. So this is straightforward. So you say, okay, 4. If you go from here, I can collect 4 fishes by the time I reach the destination. And 2 from me, 6. Highest value path from here is 6. You start filling this, forgetting about what's there. It'll come. Isn't it simple? Nope. You only keep what again? Yes, you could. Implementation, you definitely can be more efficient. I absolutely agree. I think the thinking is what matters far more as well. And that is just dynamic programming. Nothing to do with how do you approach problems. But you get cued into that when you come from recursion side. When you know what is a subproblem, when you know what cache is being built, then you know that why am I actually building a cache? Why don't I just start from the other side, use the values and keep filling it up? That is really the whole point. Question? Which one?
The premise was that it's better for you to work for, I guess, a higher level or more recognized company at that time.
Yeah. Depending on where you are in the life, I think. Depending on your life stage, it's usually. Possible. I guess my typical belief is that at least once in your career, work for a top brand name. You may stay there for 2 years. Suck it up, get all the cash and move. Because you have that brand name on the resume that helps you forever. All right. All right, guys. Thank you very much. Bye.